Hello everybody, my name is Adam Hurd and I'm the lead mentor for Team 973. This video is the first video in a series of videos we're doing as part of a new program, the 973 Remote Assistance and Mentorship Program, or RAMP for short. We're going to focus on all sorts of topics and lessons for teams, kind of work on whatever people ask for really, but since we just posted this today, we haven't received any feedback obviously, and instead we're just going to focus on some SOLIDWORKS tips and tricks I like and kind of a design style. So we're going to do this by looking at a West Coast drive, and we're not really doing any design lessons here. These are all SOLIDWORKS lessons, and a lot of these are ways I like to draw things to make it quicker and easier to edit. You're often working with people who aren't quite experienced, so I draw things differently for the team than I would at work, because it really is a different environment. So I like to make things as reflexive as possible and easy to understand as possible, and I like to do almost the entire part in the first sketch if I can. So we're going to start by drawing a side rail, and instead of actually starting this as a tube, we're going to start it as a front view. And I like to do this on parts where things get a little crazier, so you can have one nice sketch that shows everything. So I'm going to start by doing this vertical line at the origin. This is what I use actually to control our wheel drop. So as you dimension drop, your inner bearing block goes down and your outer bearing blocks go up, rather than dimensioning from the edge of the tube or something like that can be a little more confusing for other people. And then it's nice because you have this 3/16 number. You don't have to come in and do any math or thought to get your wheel drop. You just change that and that's your wheel drop. I mean, it literally is what that number is. So next I'm going to, don't know why SOLIDWORKS is freaking out a little bit here. We'll just wait for that to calm down. Hopefully SOLIDWORKS doesn't crash. Okay, now we're good. So if you're going to do as much as possible on this front view, you really want to show as much as possible. So I'm going to add wheels in here. These are going to be Vex Pro traction wheels with blue nitrile rough top, which comes out to about 4.3. Ooh, did not mean that to be horizontal, so we'll fix that. Make these equal to get equal spacing. Make that horizontal, and make them horizontal from there. So I like to mention on chain spacing, so 12 inches is a good number for 25 chain. You can see we still have quite a bit of room left of that rail, so we could come back later and make that more aggressive, but we'll keep running from here. Now I'm going to start drawing our outer bearing blocks. You notice I like to do a lot of construction geometry and relations to equate stuff so that I don't have to dimension as much as possible. Anytime you can do something with construction geometry, I feel you really should, to minimize the number of dimensions that you have to change if you want to come down and change something down the road. Okay, so now we have these slots at the right height. Obviously they're the wrong length. Ooh, very wrong length there. And what I like to do with these is, instead of actually dimensioning this block, I like to draw a block at the wheel and then dimension kind of the functional dimensions from there. So I'll do this left edge at about 50 thou. That's just to take up kind of any manufacturing errors. In this right edge, oops, oh, not, okay, go back a step. This right edge at 250. That's what is doing intentioning. Now, if you're less confident in your stuff or you want to change stuff later, obviously you can do a longer bearing box slot. We kind of nailed this stuff the first time, so these numbers work for us. I wouldn't hesitate to make your slots longer if you feel like you need that, though. So now we have most of what's going on. I would like to put my gearbox holes and that kind of stuff there, my tensioner holes, but we don't have that information right now, so we're going to skip that. We can always come back. So I'm going to extrude this. Now, I feel you should always do stuff mid-plane. Oops, not trying to make a variable there. What, am I hitting the wrong key? What's going on? Oh, I've turned off numlock. There we go. Back in action. But SOLIDWORKS is freaking out a little bit, so the video program I'm using, for whatever reason, is causing SOLIDWORKS to lag really bad, so I apologize for that. So I do things mid-plane to put as much symmetry into the part as possible, and hopefully this does not crash. Let's wait for this to finish up. So even if your part may not be symmetrical in all of its features, you probably have some features that are symmetrical, and putting those around the planes of symmetry makes using construction geometry or mirrors or revolves easier to do. I feel like if you have to come in down the road and add a reference plane just to do a mirror, you've probably laid your part out wrong. God, this video program is really dragging. There we go. Okay. So I like to name my features. It doesn't have to be anything perfect. Just enough that yourself in the future or someone else with a little bit of knowledge can come in later and edit stuff. So you'll see I'm going to cut this tube out now. I really like using offset entities for this. It's real fast. You can do this with one dimension then. And just cut that through all. Make sure you're not doing this kind of stuff blind, because then if you do come back and change the length of your tube, you have to change that number. So I do see a lot of people do blind, 12-inch cuts for a 2-inch part just to kind of solve that problem, but through all really is the right solution there. Alright, so that is our side rail. So before we do anything more on this, I'm going to start kind of on the assembly. So we're going to make our cross member now. And this is a good part where I actually do like to start by drawing the tubing first. And I think the best way to draw tubing is use the center point rectangle, dimension your dimensions, extrude that as a thin feature with the thickness you want. We're going to go 16th wall here. Make sure that's on the inside. Of course, mid-plane, just like everything else. And I think 24 inches probably works out here. So, go with 24. Name that cross member. So I do want a hole pattern on this. So I'll come in, and you'll see I use the construction geometry as a quick way to get horizontal or vertical relations sometimes. It's not inherently right, but it's not really wrong, and it really saves a lot of time for me. And then we are going to linear pattern this down the length of the tube. So it should be 47 holes, yes. Alright, so now we can start making an assembly and call that frame. So, make assembly from part, do a little thumbtack, place the parts. You notice I purposely did not put that at the origin. I'll explain why in a second. Just like in the parts, I like to build in as much symmetry and logic to the assemblies as possible. So I made a lot of things by their planes so that it kind of averages out over time that this does make things easier to work on. And when we get to like doing the top robot level assembly, it's nice because you really have a lot more control of where certain things are and for checking mass properties and that sort of thing. So they're all on top plane now. Top plane with the plane of the sketch. I'm going to mate the two side rails together. You'll notice I'm going to do one backwards because the side rails will end up non-symmetrical in and out. And I will do the same thing for the two cross members in case there's any non-symmetry that comes up later. I hate having to come back later and change the direction of a tube and assembly, which might have a whole bunch of mates at that point. So now you can do things like take the right plane of this cross member, make it the front plane there, and take the right plane of a side rail, make it the right plane there. Now you're really starting to lock things in. These side rails are still loose this way though. Let's see where that plane is first. A great tool I love that I unfortunately did not find out until about 2 years ago is the Symmetric Mate, which lets you mate around a plane. And what's really nice about that is it lets you dimension what you really care about. So let's say here I really want to dimension my wheel wells versus the inner dimension, so I can come in and do that. Let's go with 3 inches here, so doing some giant wheels and see how that works out. So now if I did all that right, we should have a fully constrained assembly. We do. Cool. With the origin placed in the center of all those. Alright, so I'm going to turn the origins off, save that. Where do we go from here? So I like making the frame a sub-assembly too, and you'll see that down the road why I like doing that. I didn't really have a plan for these videos coming in, so I may stall a little bit halfway through, hopefully get better at these in time. Add the whole pattern to this guy. So for parts that I know are on half-inch increments and are never going to change, I get super lazy dimensioning these holes and do this because that saves me a lot of time. And I'm actually doing things a lot slower for these videos than I would usually, partly because the video program is lagging, partly because I want you guys to see what I'm doing. A lot of these things I do let me save, a half second at a time, and that really adds up during marathon CAD sessions, I think. This should be, oh, I don't know what's going on. Oh, it's complaining about that decimal. 59 holes. Yes. Save that. Oh, I guess we want to put some fillets in here, so we get to use one of my favorite tools. We do 1/4 inch end mill there, so 1/8 inch fillet. The fillet wizard saves so much time. Unfortunately, I think it may still be this way, but if you do a configuration, SolidWorks won't let you use fillet wizard, and that's a real bummer. But this is not a configuration, so that's not a problem. So we look at our frame, that looks good. Maybe let's do our gussets now. I'll show you how I like to draw some of our gussets in a way that can save a lot of time. Once again, this is stuff that I would not do at work because people would make fun of me, but I will do it in FRC without shame. So you can see I just drew a bunch of lines. I'm going to make those half-inch spacing. Then I'm going to put holes on those lines. Maybe I want another line, looking at this now. And believe it or not, this is how we draw most of our gussets, because it's really fast. At one point in time, I liked drawing gussets at the assembly level, but with how clean our hole spacing is, I found that often just made things harder and more confusing, and it's quicker to lay stuff out like this. Actually, let's make those holes 196. I also love to abuse the, I do not have my tool set up on this computer, by the way, so that's going to bug me a bit. I like to abuse the slot tool for drawing gussets, because you get stuff already kind of filleted for you. Make those 0.25. Let's say we're not going to pocket this guy, and we just select what we want. And just out of habit, I do make this stuff mid-plane, just kind of muscle memory. I guess we got a free pocket there. We'll take that out. And we'll name that gusset. Go back to our frame. Do that guy. Now, some people in this situation really like to heavily use mirrored components. And maybe I'm just wrong about this stuff, but sometimes I really get myself in trouble with mirrored components. So when I can, I actually do place stuff manually. But if, just like any of the stuff I'm doing, if you feel like you have a better way of doing this, I would love to hear that. I'm always stealing SolidWorks tricks from other people, and that's one of my favorite things to ask a new person I work with is, like, what's your top 5 favorite SolidWorks tricks? And now the video program's lagging me a little bit, so we'll wait for SolidWorks to catch up. And it's not catching up quick. That is unfortunate. Kill some time. Oh, there we go. Okay, yeah, so I like asking people what their favorite SolidWorks tricks are, because there's just so many of them. And it's also interesting to see different people's styles in SolidWorks. Cool, that one worked. So just make these gussets. You'll notice I'm not putting a gusset on the bottom side, and that's because I do like to use the belly pan as that gusset. So now, assembly's still totally constrained, looking good. And I guess we can start making our drive. I'll admit I cheated and have some things done already. So I'm going to make assembly from assembly. I'm going to put that frame in there. Turn off the origins. Right plane, right plane. Oh, forgot to float it first. Come down and change that to float. Hitting the wrong things. Right plane to right plane, front plane to front plane. Not mating top, and you'll see why I do that in a little bit. So now I'm going to insert some components. Browse. Let's get our bearing block in here. And you'll kind of see a similar style of mine show up in a lot of things to do. And now it's lagging again. There we go. And that I really like to dimension things like this together a lot before I really place them to the frame to eliminate as many dimensions as possible, really. And once again, I've always felt like mirror does not work out well for me in situations like this, but if you disagree and have a good example, please show me. I would love to see that. So you see I flipped those around because there is some non-symmetry in those bearing blocks. Actually, if you zoom in and look, there's an air gap on this side. And what that is this bearing block is 990 thou long, so that when you clamp 1 inch or nominally longer than 1 inch tubing with powder coat and stuff, you really clamp it. I also like this because our bearings are actually in that solid block. These face plates don't touch the bearing at all. You can kind of see that if we zoom in here. That means no matter what the thickness of our frame is, if we get different tubing one year, different powder coat, it doesn't affect our shaft length at all, which is real nice. Those bearings stay the same dimension apart. And what we do is that inner plate is one that we tighten real good and lock tight and then never move again. So that is why we like to have the outer plate be the one with that 10 thou gap. So now you can see that when I move one bearing block, they all move, and that's nice. Oh, I forgot one thing I like doing, and that's coming in, of course, and using one of my favorite relations once again, the symmetric. Let's go to Advanced Mate, Symmetric, and this should be the right plane? Yes. So now that if I come in, oop, I guess we missed one. Let me rebuild and see if I did miss it. Yep, we missed one mate I wanted to do, and that's this guy, concentric to that guy. So now if we just dimension one bearing block's location in terms of tension or travel, they all are set, and I think that's really cool. So just to cheat a little bit and show a principle, I'm actually going to add a bearing block. You know what? No, we'll come back to that. So we have this in. Let's save this and call it drive. What I like to do for assemblies where it makes sense, and drive is definitely one of my opinion where it makes sense, I want this top plane to actually be the floor of the field. So I'm going to cheat a little bit right now. Later I would actually like to do this with the wheels in there and make it tangent, but I'm going to do some mental math and dimension that to the floor as the wheel. So we know it should be 4.3 divided by 2 minus 1 plus half of our wheel drop, which is 3/32 then. I will come in later once we get wheels and dimension that to be tangent so that the wheel sets that. And now what we've done is if we come into mass properties, our Z mass property is placed exactly on the top plane. And I'm phrased that horribly. When you come in and check mass properties, the dimension to the center of gravity in Z is the actual dimension from the floor, not some arbitrary height that you then gotta, oh, our origin's 4 inches off the ground, let me remember that, let me think about that. No. Then when I make this into the top robot level assembly later, the top robot level assembly has the origin at the floor with the front and right plane centered so that, Y and X have a similar effect. It's your CG from the center of the robot, left, right, and front, back. So if you get 2, 2, it's forward 2 and left 2 or whatever that coordinate system is. And if you get a Z of 6, it's 6 inches off the ground, not 6 inches plus something. And it's little things like this that I think really make things just easier. And anytime you can save a couple minutes, you really should. So now we're going to come in and make a single speed gearbox. And this is the one that really can get us in a lot of trouble. So hopefully this works out well for us. So I think the origin for a gearbox should be the output bearing, so I'll start with that. Maybe I'll pocket this gearbox, maybe I won't. I'm always afraid of teaching people pocketing because it seems like people focus more on pocketing than design, and I think that's wrong. Also, you'll see in here that I'm going to cheat and not use Hole Wizard, and I'll explain why when I get there, then show you that you can still kind of do this style with Hole Wizard. And that's, you know, in FRC, at least for our team where we use the same few fasteners, it's easy enough to not use Hole Wizard because you know the size of everything, and it makes it easier to do things in one sketch. Then I'll show if you really want to use Hole Wizard, and Hole Wizard is really good for a lot of reasons. I'll show you how you can still do that with this style. So I have no idea what gearing we're going to do, so I'll just start making some stuff up. This might put us at an impractical speed, but hopefully it doesn't. So I like modeling the OD of gears, and for 20 DP, that's going to be the tooth count plus 2 divided by 20. So both these gears are 50 tooth gears. Let's say we have a 20 tooth pinion here, so that would be 22 divided by 20. No, let's do a 14 tooth pinion. So 16 divided by 20. And that would mean actually that I probably have a 3/8 shaft up here, so I'll come and make that 7/8, which then means this shouldn't be equal anymore, and I'll make that 1 and an 8. I start with stuff nominal and come back in and kind of tolerance things later, so these are not the dimensions we'd actually cut our bearing block holes to. Most of our shops actually don't work off the SolidWorks model, but we give them that for reference and fixturing, but they actually do dimension things to the drawing, and our kids work that way too, so accidentally dimensioning things nominally here is really not a big deal. So let's do our gear spacing. Not sure what happened there. And that's going to be the sum of the teeth, so 50 plus 14 divided by 40 plus the center to center. Sometimes I will make the circles tangent and have that, set that, or I'll come in and do a line there. I've been doing this recently. I'd like a cleaner way to do this for everyone to understand. So if anyone has some real cool ideas that are quick to do to link this kind of stuff, that'd be great. I used to link kind of the ways I was talking about, but it took a little more time, and I don't know that I ever changed gearing that much to make it worth it. Although when I would do like an arm gearbox or something where I would really iterate gears a lot, I would invest the time up front to do that so that when I changed my gear ratios, it would go quickly. And often what I would actually do there is put in the design table using Excel that actually was the full system model, you know, percent stall and everything, and I would do my iteration in there and have that change my gear sizes, the center spacing, everything. So it was really quick and really cool for that kind of stuff, and I'll dig up that file and post that if I can find it. I'm afraid I actually don't have the raw SolidWorks file for that gearbox though, but that is a cool trick. But let's stay on topic here. So now we have a 50 tooth gear not driven by anything, driving a 14, driving a 50, which was the output. So we need some sims on here. So you'll see I love to abuse construction geometry. So these two lines represent the center to center from the sims there. We're going to go with a 12 tooth, so that will be 12 plus 50 divided by 40 plus 3 again. Draw some sims in here. I like to draw my sims at 2.55 just to make my models have a little more comfort room in them. But I don't think I've ever measured a sim bigger than 2.52. But if you really want stuff to fit, you should measure your own sims and not trust what I say in a video. This video program lagging is killing me. And what's cool about this gear spacing actually is it looks like we could fit a third sim up there easily, although we're not going to do that today. And if you have any questions or feel that I am doing stuff too quickly or not explaining some of these things, shoot me an email at that 973 ramp address and I'll gladly go over it. It's been so long since I've learned SolidWorks, I kind of forget what's easy to learn and what's hard to learn, so I think I'm hitting the important stuff for you guys, but if I'm not, just let me know. So you can see, once again, using a lot of construction geometry to minimize dimensions. And also I like to, you know, dimension what you're really changing time to time. So, you know, I could have made this equal to that, but I feel like that's kind of a different hole, and maybe we would want one to be 196 or something. Maybe we would change later. So I don't like to link too much stuff because you can get yourself in trouble. I'm going to use this midpoint line to link that vertical, and that's kind of a hokey trick, but that's cool because now you can rotate these holes however you want. And Maybe we'll do these vertical. That looks decent now, and we'll set the sim at some height. I'd usually lay these things out a little more intelligently, but I'm doing this kind of quickly for you guys. So now we have the start of the gearbox. So draw the outside meat now. I'm not. Why isn't that snapping too? The shape of a gearbox and pocketing is something that I feel really is hard to decide up front, so I'll try stuff, see if I like that or not, come back and try more stuff. Today I'm not going to spend too much time on that because I'm trying to focus on more important things, and I feel like if teams are really getting into designing their own gearbox plates and pocketing and all that, they probably don't need too much of my help. So sometimes, depending on the size of the gearbox, I like to make this cover the gear. Sometimes I don't. I guess today I am. You'll notice I didn't dimension these circles out here, their size, and that's because I just made that right side vertical. See how that looks. That kind of gives you a lot more material than you need, but I'm running with that for now. Alright, so now we have a gearbox. Oh, one last thing. We do need to add, at least for us, the bolt circle that connects to our bearing blocks. And this is the case where I will absolutely use Hole Wizard to get the countersink. And what I like to do when I'm doing this style gearbox for holes that are later then going to be Hole Wizard is I will dimension them implausibly small so that if you saw them you would know they're wrong. And then that gives you the centers for when you come back later to do Hole Wizard. So click stuff and get stuff working. Cool, looks like this worked pretty easily. 0.25 mid-plane. The 1/4 inch plate we actually get is 0.26. I'll make that slight change because that combined 20 thou can get you sometimes depending on your design. So now we have this gearbox. I'm not going to populate it with gears and stuff today. I feel like I proved enough in that sketch that this clears, especially if you poke around there a little more. I might not have actually. Usually I spend a little more time at this level really making sure stuff clears, but it looks like everything clears here. So I'll come in and do some of the Hole Wizard-y style stuff I was talking about. So I want some countersunk holes in here, so I'll come in and I'll grab Hole Wizard. Number 10, normal, cool. Everything's set up how I want. You can tell I only really do stuff with 10s on this computer. So there's that. And we're lagging again. Alright. This is unfortunate. If anyone has a recommendation for a better screen recording program that doesn't lag SolidWorks, that'd be great. I'm using Cam Studio right now. That was just the first one that popped up on Google. I've never done this before. Although, oh, there we go. Looks like that took it. Okay. Also, I guess our gearbox do have counter bores, which would obviously have to be separate from the first sketch. And this is for a tubing to use as standoffs. This is something we totally ripped off of 2D4, 968, and those guys. And it's really nice. And I think RC is doing this on the gearboxes he sells now. So we do that, I want to say 100 thou meat left, so I do offset from surface. Alright. So we're going to make this into an assembly and just call it a fake gearbox, even though we're not going to put gears and stuff in it. Maybe we'll do that in another video. So maybe this is an 1.25 inches apart. Just making these numbers up. It sounds plausible. Actually, I think with Vex gears, 1 1/8, because you have 1 inch between the two gears, they're 1/2 inch each, and you have a 1/16 per bearing flange. So that should be good there. Once again, you see me making a lot of stuff with planes. I really like doing that. Oh, and you can see that I actually dimensioned that 1 1/8 wrong. I would have wanted that to go the other way, so let's fix that. That's this guy here. Oh, no, that's not right. Mate alignment, flip dimension. There we go. Then now I'm going to want to mate the right planes. Cool. I don't have any sims set up conveniently already, so we're just going to leave that without sims. You guys can all trust, maybe standoffs would go in there and yada yada. Oh, so I am going to insert half of a bearing block. I'm going to be really lazy and use this CAD file. No, I'll do it right. Oh, that's not what I want. I need these two guys. There we go. There's that. And that. So the gearbox style that we've used for years uses our bearing block as our center mount. Some of the ones in the market and some of the ones that other teams have done do that, some don't. Not saying that's right or wrong, it's just what we decided and it works for us. And I'm lagging again, unfortunately. And if you're particularly interested in our West Coast stuff, all of our robots, probably 2010 to 2011, and then to a lesser extent the 2013 drive, would be great ones to look at. And those are all posted. You can get that in my signature on Chief Delphi, and I think they're on our website as well. Alright, so there's that. Let's throw some bearings in there. Gotta love hex bearings. Getting that error. We actually run this bearing on the outside of this plate because if you look at how, this won't be fully detailed here, but if you look at the shaft stack up, you need something keeping your shaft from coming out this way, so a snapping on that back edge is what we do on our stuff. Alright, so here's our imaginary gearbox. Let's go back to our drive assembly. We're going to insert 2 of them. Oh, and in case you missed it, now we know what we want to do for our gearbox spacing for mounting, so we're going to come in and add that. So we decided it was going to be those holes on a 4.5-inch center. And then for tool axis, what I like to do is just come into the second feature. Because we only bolt through one wall, you can actually get a lot better connection that way. Unless you want to go in and add tubing in that wall, crushed tubing or something. And this may look tedious, but those bolts are so long, and we do socket heads, that this is really easy for the kids to get in there and do. And the bolt is too long to actually lose in the tube, so not a problem. So I do like bolt access or something, just enough so someone later will understand the stuff. So now, if we come back in this assembly, everything should work out. Pick up the 2 bolt holes. Around, and just like everything else, I'm going to come in and I like using my right planes and my top planes to do stuff. So there's that. So what next? Maybe let's add some wheels in here. Another part I cheated on. So I have a Vex traction wheel configured how we want it already. So I'm going to come and add 3 wheels. You guessed it, just like everything else, I'm going to come in and mate all these wheels together as possible before mating them to the assembly. And it's lagging again. Usually I would have shafts in here before I mate stuff, but I'm going to be lazy and mate bearing to bearing. And we're lagging once again. Save before we lose everything. Looks like it's complaining about something in the frame. Rebuild, see if that fixes. No, okay. What have we done in the frame to get an error? I don't believe it was complaining earlier. That is really weird. I don't know what caused this. That's really unfortunate. So I'm going to ignore that for now, even though that's kind of bad practice. That was totally fine last time we touched it. Not really sure why that's complaining. So we'll get our wheel set up in here. And we're lagging again. I wish I'd been a little more prepared for you guys and I would have had shafts and sprockets. But I was not, unfortunately. So now we're going to come in and use, once again, one of my favorite tools, the Symmetric, this time across the front plane, so that we can come in and, let's say we're going to dimension this dimension, because we're going to do some nominal spacer maybe. So let's see how a 1/4 inch looks there. The top view. At first glance, that looks good. We actually replaced these nuts with thin profile nylock, so we'd have that space. Also, these wheels could just have the fasteners on the other side. So this looks like a problem, but it actually is not. So in the interest of keeping these videos short, I'm going to stop at this point. Maybe the next video we'll add in shafts, sprockets, and that kind of stuff. So if you have any ideas, we'd love to hear them. Because I'd really like to hit whatever you guys have questions on. So thanks for your time, and hopefully you guys got something out of this. And also, we'll end up posting the CAD files from each of these lessons if you want to play with stuff yourself and look at that sort of thing. All right, thanks everybody.